My name is Hui Li. I'm from University of Illinois at Urbana-Champaign. My advisor, Ryan Sriver, is the PI of this project. Today, I'm very excited to present to you results from our Blue Waters project, analyzing tropical cyclone and climate interactions using the Community Earth System Model CESM. So, tropical cyclones, they are these giant, brutal storm systems over the ocean. And they could cause major coastal damages and pose tremendous threats to lives and properties in the coastal area. These photos are just a glimpse of the aftermath of Hurricane Sandy in 2012, which costed United States $65 billion. And in the face of climate change, more and more people begin to worry, will tropical cyclones get worse in a warmer climate? And in fact, not only that, a lot of studies have recently found that tropical cyclones could in fact actively contribute to the Earth's climate through their interactions with the upper ocean. And this tropical cyclone's active role in the climate system is what we are it's what we are focusing on in this project. So let me first start by explaining how this works. Tropical cyclone, how can they play an active role in the climate system? So we know when this giant tropical cyclone blows over the ocean, it causes violent vertical mixing that brings the cold water up to the ocean surface and injects warm water down into the ocean interior. And this mixing process could change the temperature, the ocean temperature profile in this figure in this corner. The x-axis here is the ocean temperature, and y-axis is the ocean depth. The black curve here is the ocean temperature profile before the tropical cyclone occurrence, and the gray curve here is the temperature profile after the tropical cyclone passage. The corresponding temperature anomaly, which is the difference before and after the tropical cyclone, is shown in figure C here. So we can see, as we discussed before, have a cold anomaly in the near surface ocean from surface to about 40 meters depth, and then we have a warm anomaly beneath. And this upper surface cold anomaly could be observed by satellite along the tropical cyclone track, as is shown in figure A here. So we have seen that tropical cyclones cause this violent mixing, and they causes temperature anomalies in here. And then after about 30 to 40 days, this near surface cold anomaly could actually be restored to pre-storm condition through the surface flux adjustment with the atmosphere. But the warm anomaly beneath could persist for a much longer time. So the result of this tropical cyclone-ocean interaction is a net heat gain in the ocean. This has important implications for global ocean heat budget in transport, as well as large-scale circulations in the ocean and atmosphere. And this is why we care. So over the past decades, a lot of studies have supported the idea of tropical cyclones have the potential to alter the large-scale circulation pattern in heat transport in the coupled atmosphere and ocean system. So studies have found that tropical cyclones could significantly affect ocean heat budget and meridional ocean heat transport, mainly in the tropical area, and also atmosphere circulation patterns such as Hadley circulation, and also climate variability. They will contribute to the El Nino-like ocean temperature patterns. So a very interesting conclusion is that these extreme weather events, this relatively small scale and transient weather events, could potentially affect the large scale climate. So understanding this tropical cyclone climate interaction can advance our understanding about the climate dynamics and variability. And this contribution to the climate system may have important implications for anthropogenic global warming through feedbacks in the coupled system. So there are several key challenges when we're trying to answer these questions. And tropical cyclone climate interactions are currently largely unexplored in the current climate models. Why? Because we need very high resolution global climate model to resolve small-scale features in tropical cyclones. And we need long simulation time, decades of simulations to construct a tropical cyclone climatology in order to diagnose their effects. And we also need active coupling between the atmosphere and the ocean to correctly capture the interactions and feedbacks within the system. And all these things require one thing. We need more power. So here comes the blue waters. Why blue waters? We investigate the tropical cyclone and climate interaction using the state-of-the-art comprehensive Earth System Model, Community Earth System Model, or CESM. And blue waters is one of the supported machines for CESM. The second reason is that the simulation, as we mentioned before, it requires decadal scale, high-resolution configurations. We need 25-kilometer gray spacing for atmosphere and 10 to 100-kilometer gray spacing for the ocean in order to resolve this important small-scale features. And this means it's very expensive. We need 230,000 core hours per simulation year, and we will need 1 million node hours for the whole simulation. And the simulation will require petascale computational resources. Another feature is that the code is has high scalability. This figure at the corner shows the scalability test we did in our past allocation time. We see that the atmosphere, the most expensive component, the atmosphere model, has very high scalability. It uses a spectral element dynamic core. So when we use about 800 to 1,000 nodes, we can get a throughput about 2 years per simulation day. 2 simulation years per day, sorry. And then we also have done a lot of code testing and load balancing through previous allocations, which has laid some groundwork for the new simulations. So thank you, Blue Waters. So Blue Waters provides a unique opportunity to analyze tropical cyclone climate connection using a state-of-the-art comprehensive Earth system model. Okay, now I want to move forward to show you some results. To show you some results from our ocean-only simulation. This work has been submitted and under review right now. And this work is actually done through our past allocation. So we have seen that tropical cyclones have the potential to influence large-scale climate dynamics and circulations, which has important implications for future climate change projections using climate models. And we want to ask, are these features captured by the current climate models? And if not, what are the factors that could affect the model scale of capturing these processes? So in this project, we particularly want to ask, what is the effect of the ocean model resolution on these processes? So in order to do that, we use the tropical cyclone winds to force the ocean model. The ocean model we're using is the CESM Ocean Component POP2. And we have 3 sets of simulations where we vary the ocean horizontal grid spacing. So we have a 3-degree ocean, a 1-degree ocean, a 1/10 of a degree ocean. A degree, I mean latitudinal degree, it's about 110 kilometers per degree. And for the tropical cyclone winds, we detect a tropical cyclone forcing from a fully coupled CESM simulation that was done by Justin Small et al. In 2014 in National Center for Atmospheric Research. This simulation, they use 25-kilometer grid spacing atmosphere and 1/10 of a degree ocean, which is very high resolution. They found that at this high resolution, you could actually simulate tropical cyclones spontaneously within the model, meaning that you don't need to add in any disturbances or any special treatments. Tropical cyclones just sprout out in the model. So you look at the results, you can see there are some storms in it. And we developed a tracking and detection and tracking scheme in order to find all the tropical cyclones in the model output. And very happily, we find that this model can actually simulate tropical cyclone characteristic in agreement with the observations. This is the tracks we detected from the model. The colors indicate tropical cyclone intensity. So we could see the model is able to simulate realistic geographical distribution and also in very intense storms up to Category 5. And the number climatology is also very realistic. So we had this tropical cyclone winds. What we did is that on each storm day, we take a snapshot of the tropical cyclone winds centered at the storm center. And then we take all these winds and we blend it with the normal year forcing condition. The normal year forcing, you can think it as a long-term average atmospheric boundary forcing. It includes near-surface winds and surface fluxes and all that. And in the original normal year forcing, we do not have any tropical cyclone features. So by blending these winds with the normal year, we have a full control of what storms we added in the simulation. So now we have 3 sets of simulation. We have a 3-degree ocean, 1-degree ocean, a 1/10 of a degree ocean. And then for each simulation, we run the model for 5 years. And then we branch the run into 2 rounds. The first one is a control run, which is basically the spin-up run. We still use the normal year forcing condition. And another run is a TC forcing run, where we add in the tropical cyclone winds we just detected. So by comparing the results from the TC forcing run, the control run, we could diagnose the effect of tropical cyclones. And by horizontally comparing these 3 sets of simulations, we can test the sensitivity of these responses to ocean grid resolution. So let's move forward to see the results. First of all, we want to see how the ocean actually sees these tropical cyclones. Okay, this figure at the top is the tropical cyclone winds we see from the high-resolution model. It's a very intense storm with the maximum wind of about 58 meter per second. And these are the surface wind stress that are seen from the ocean models. We can see that although you're forcing the ocean models with exactly the same tropical cyclone winds, you could get very different ocean responses. The 3-degree ocean sees a very slight curve, and then the 1/10 of a degree ocean could not only simulate realistic tropical cyclone wind structure, but also the intensity. That means that even if you have a perfect atmosphere model, you push it to very high resolution, but if an ocean model resolution is not high enough, you are not going to get the correct responses, especially the heat that get pumped into the ocean. Okay, now I want to see some surface. SST stands for ocean surface temperature, sea surface temperature. So this is an example of the tropical cyclone in the model, and this is the time series of the surface cold wake. We just see, because of the mixing, there's a cold wake on the surface. X-axis is the days relative to the storm passage, and the y-axis is the temperature anomaly. The temperature anomaly is defined as the difference between the control run and the TC forcing run. So what we did is, on the day of the storm, we take a 6-degree by 6-degree box over this tropical cyclone, over this area of ocean, and we calculate the average temperature. And then in the following days, tropical cyclone move along, but we kind of monitor the temperature changes in this specific area, right? So we can see that at the day of tropical cyclone occurrence, we have a cold anomaly happening, as we've seen for the tropical cyclone cold wake. Then after about 40 to 60 days, this cold anomaly kind of restored to the pre-storm condition, right? But this difference is very different. This response is very different among different models. So the 3-degree model has this cold anomaly like this, and the 1/10 of a degree is the black line here. So you can see that these maximum cooling on the ocean is different among the 3 different models. And this is true for the one case, but it's also true if we look at the global response. This is all when we analyze all the tropical cyclones and get to an average response. For the 3-degree model, 1 degree and 1/10 of a degree model, the black line here, the thick line is the global average responses, and different colors represent storms in different basins. Okay, that was the surface, and let's look deeper into the subsurface. Again, this is a storm with a maximum wind of 68 meter per second, a very intense storm in the model. And these are the ocean subsurface responses. So x-axis, again, is the time relatively to storm passage, and the y-axis is the ocean depth. And the colors indicate the ocean temperature anomalies between the TC run and the control run. So interesting, we could see all these processes we discussed. In all 3 models, we could see some cold anomalies at the near surface, some warm anomalies injected into the ocean in the subsurface down to about 100 to 200 meters. And also, if we, the patterns are, all the models are able to simulate these patterns, but the magnitude of the signal is very different. We get a much stronger signal in the 1/10 of a degree model. And if we look closer at the 1/10 of a degree, we can see very interesting processes. Again, we have upper ocean cooling, subsurface warming, and then we can see the cold wake recovery through surface fluxes, but the warm anomaly persists for as long as 6 months and beyond. And we could also see some heat get reabsorbed back into the ocean mixed layer and ultimately would be released to the atmosphere. This is due to the seasonal variation of the ocean mixed layer. So in the winter, the ocean mixed layer extends downward and it absorbs some of the heat that's previously pumped down and then get it back to a mixed layer. And mixed layer would just exchange heat with the atmosphere. So eventually this heat would not account for the long-term heating effect. And this process, this reabsorption of heat into the mixed layer is not captured in the 3-degree and a 1-degree model. Okay, here are some animations of the temperature anomalies. Upper two panels are SST from 1 degree and 1/10 of a degree. Lower panels are temperature at 100-meter depth from 1 degree and 1/10 of a degree. Because black dots are tropical cyclones. And we can see that at 100 meters, we can see some equatorial waves that are transporting heat eastward into the East Pacific. And this equatorial wave are excited by tropical cyclones. And this heat transport is gonna contribute to the El Nino-like ocean temperature patterns. And we can also see some ocean surface cold waves along the tropical cyclones. And then as days goes by, as we come to the end of the year, we can see tropical cyclones indeed have some food point, some accumulated effects on the global ocean. And this effect is more chaotic in the 1/10 of a degree model because at 1/10 of a degree, you can fully resolve the ocean mesoscale eddies, but these eddies has to be parameterized in the 1 degree and 1/10 of a degree model. Apparently, this fully resolved ocean eddies can transport heat everywhere and result in this kind of interesting heat distribution at the end of the year. Okay, and then we want to have a quantitative estimate of how much heat is pumped into the ocean that could have long-term effect on the climate. So we have talked about tropical cyclone heats the ocean, and there's mixing that homogenize the upper ocean, which pumps heat below the ocean mixed layer. And in the winter, the mixed layer extends downward and absorbs some heat back into the mixed layer, and only the amount of heat that is below the annual maximum mixed layer depth could really have some long-term effect, right? So we want to quantify how much heat that is pumped below the annual maximum mixed layer. Yeah, that's a median. And so this is the equation we use to calculate the ocean heat uptake by tropical cyclones. It's essentially a volume integral of the heat anomalies from the ocean. And then the figure here is the temperature anomalies without and with and without tropical cyclones. So this is the depth of the annual maximum mixed layer, and then we integrate this heat downward, firstly to 100 to 300 meters to, and this is the result of how much heat is pumped into between these two layers. And this is the time series of the heat from day 1 of the year to the end of the year. And these are the amount of energy, amount of heat that is below that is between these two layers. And we could see that different models have different responses. The highest resolution model, the 1/10 of a degree model, has a higher value at the end of the year. And it's actually a very big difference here. And then if we want to explore more, we integrate this heat from this maximum mixed layer down to about 1,000 meters. We get a result like this. So at the end of the year, the 1/10 of a degree model could pump 4 times 10 to the 21 joule amount of energy into the ocean. This is the effect of tropical cyclones, like if you look at from annual time scale. And this accounts for 10% of the basin scale ocean heat content. That's a huge amount. Okay, so that's the results from our ocean-only simulation. We have examined the effect of ocean model resolution on TC ocean interactions using an ocean general circulation model. And we found that the models simulate key characteristics of transient ocean response to tropical cyclones, and these responses are sensitive to ocean grid resolution. And our findings indicate that tropical cyclones significantly contribute to the global ocean heat budget and pointing to important connections between tropical cyclones and ocean dynamics. And we find that tropical cyclones have the potential, because they have the ability to inject heat into the ocean, they have the potential to influence ocean dynamic dipycnol mixing budget, seasonal to interannual climate variability, such as ENSO, and large-scale circulation patterns in the atmosphere and ocean. And that work was done from our previous allocation. In the current allocation, we're actually running a fully coupled high-resolution decadal scale CESM simulation with a 1/4 of a degree atmosphere and a 1 degree ocean, because 1/10 of a degree ocean is too expensive and we only get 600,000 node hours. Just saying, we need more. Yeah, and we are gonna explore these connections in the current climate and the future climate. And also, the results from our current allocation would help us to answer some fundamental science questions, like what is the impact of tropical cyclones on the regional to global scale ocean atmosphere circulations, and are these dynamic interactions between tropical cyclone and the ocean atmosphere system that could affect global climate variability and trends. And the results of this work will improve our understanding of the nature of atmosphere-ocean interaction within the coupled models, which in turn will improve predictability of tropical cyclones and reduce uncertainty in climate change projections, especially at the time when we are pushing towards very high resolution atmosphere models. Okay, that's all I have. Thank you.